This lecture is part one of a lecture on section 4.4 from Math 311, a course on linear algebra at Western Illinois University. So we're going to begin talking about two very important concepts of matrices, which has to do with similarity and diagonalization. And this, of course, is connected to eigenvalues and eigenvectors. And what I want to do is start off with a few examples and then just to see how the theory flows from there. So last time we talked about how to find eigenvalues and eigenvectors, and by themselves they wouldn't be much use, but they have a lot of nice applications, and hopefully we'll see some in these next examples. Particularly we found it was very nice when if you can find eigenvectors which are also linearly independent, and not only if you have enough of those that form a basis of Rn, if you're dealing with n by n matrices, if you have a basis, some very nice things happen. So I want to start off with for our first example, I'm going to let A be the 2 by 2 matrix 2, -3, 1, 6. Okay. And we're going to find let's find the characteristic polynomial and the eigenvalues and the eigenvectors. So A minus lambda I is going to be 2 minus lambda, -3, 1, 6 minus lambda. And when we take the determinant of this, and this will be 2 minus lambda, 6 minus lambda, minus -3, which is plus 3. And so this is multiplying this out. You get lambda squared minus 8 lambda plus 12 plus 3 is lambda squared minus 8 lambda plus 15. And I think hopefully you can see that this factors nicely as lambda minus 3, lambda minus 5. So lambda equals 3 and 5 are your eigenvalues. Okay. So we plug in 3 and 5 in here. For lambda equals 3, we get -1, 3, or -1, -3, and 1, 3. And we want to find the null space of this. Okay, and it's not hard to show that we can see that x plus 3y is equal to 0. So x is going to be minus 3 times whatever y is. So we can just take take y to be 1, and we get -3, 1, and you can easily see that that's going to be in the null space, and any eigenvector is going to have to be a multiple of this. If we look at lambda equals 5 and plug it in here, we get 2 minus 5, that's -3, -3, 1, and 6 minus 1 is 1. And again, we want this to find the null space of this matrix, and we see that x plus y has to be equal to 0. So x and y have to be opposites, right? So we can see 1, -1 is going to be an eigenvector for this, and any eigenvector for 5 will be a scalar multiple of this. So these are our two eigenvectors. Okay. And we all know, so with this so far, nothing is different from the last section. But let's call these. Have a little bit of fun with this, if you call this fun. We're going to let's call this we'll call 3 lambda 1, and we'll call 5. We'll call this lambda 2. Then we'll call this eigenvector v1, and this for v2. Okay, so v1 is an eigenvector for lambda 1, v2 is an eigenvector for lambda 2. And I'm going to look at, we're going to let P be the matrix whose columns consist of just these eigenvectors. So we have -3, 1, 1, -1. Okay, which we can call, which is, again, this is just V1, V2. Okay? And before we go on, we can see that these are, P has to be invertible even before we start, because we can take the, for two reasons, we can take the determinants and we'll see that that's 2, it's not 0. But we also know that these are, these two vectors are linearly independent. We can clearly see that because they're not multiples of each other, but we also know that because the eigenvalues are distinct. Okay, so this is invertible, and it turns out you can do elementary row operations or use that little formula for 2 by 2 matrices and say P inverse is going to be negative 1/2, negative 1/2, negative 1/2, and negative 3/2. Okay, and you can check that that's true. Now, why are we doing this? Well, let's do one more thing. Let's take the product of A times P. Okay, A times P, without actually multiplying this out, we know that this is going to be A times the matrix V1, V2, and we know that we should be comfortable enough with matrix multiplication, know that the product of this is going to consist of the matrix whose first column will be AV1, the second column will be AV2. Okay, but we know that because V is an eigenvector, V1 and V2 are eigenvectors, this is going to be lambda 1, V1, and this is going to be lambda 2, V2, which is, we know that is going to be 3v1, 3v2, or 5v2. Okay. Now, if you think about this for a moment, this is actually the product of our original V, or the matrix V1, V2, times the diagonal matrix 3, 0, 0, 5. If you think about that, because this is, you just take the, you just multiply stuff out, you have, everything in this column is going to be multiplied by 3, and everything in the second column is going to be multiplied by 0 or 5, right? Okay, so, so we get that this is actually P times D, where D is going to be this diagonal matrix. Okay, so we get AP is equal to PD, and we can multiply both sides by P inverse on the left. Okay, or we can multiply by we can also multiply by P inverse on the right, and we would get A equals P D P inverse. Okay. And either way, we can see that A and D are now related by a certain way. We can take A, and if we multiply, what we have is an invertible matrix times A times the inverse of the invertible matrix equals D. And over here we have another invertible matrix times D times the inverse of the invertible matrix, and that's A. Okay. We'll eventually see that the technical term for this is that A and D are similar. And in fact, because D is diagonal, we say that A is diagonalizable. Okay, but this is we'll come up with the formal definitions a little bit later. But let's see why would we care? Why would it be nice? Well, it's nice when you're asked to compute large powers of A. Because if you were just to try to compute what A to the n is, that could be a little messy. However, if you want to compute powers of a diagonal matrix, that's very easy. You just take the powers of the diagonal elements, and 0 is everywhere else. So how does that help us? Well, A to the n now, we can replace A with P D P inverse to the n. And this is just going to be P D P inverse P D P inverse multiplied by itself n times. Okay, and we can, of course, we can see that these P and P inverse canceled out, except for the first P and the last P inverse here. So this becomes P D to the n times P inverse. Okay. All right. Well, what's that going to be? Well, now this is P. We said is -3, 1, 1, -1. D to the n is going to be 3 to the n, 0, 0, 5 to the n. And we already know what we have P inverse here. It's 1/2 and -3/2, right? Okay, and then we'll multiplying all these. When you multiply things out, I guess we'll multiply these first. We can see this will be -1 times 3 to the n plus 1 plus 0, and we have 0 plus 5 to the n, then 3 to the n plus 0, and 0 plus -1 times 5 to the n times -1/2, -1/2, -1/2, -3/2. And then when we multiply this again, what we get is 3 to the n plus 1 minus 5 to the n over 2, 3 to the n plus 1 minus 3 times 5 to the n over 2, minus 3 to the n plus 5 to the n over 2, and minus 3 to the n plus 3 times 5 to the n over 2. Okay, so this is a to the n. Okay, and this actually works out. You can, hopefully all my algebra is okay, but assuming it is, it's kind of interesting because, well, all of these are, it looks like these are fractions, but in fact, these are going to be integers. Because any power of 3 and 5 are odd numbers, so you take a difference or a sum of odd numbers, it's an even. So this does work out. All right. So that's kind of cool. One nice thing happens when you can write a relation, write A as in the form of something like this, then its powers become very easy to compute. Now that's great when it happens, but sometimes it won't happen. For example, if we look at, for the next example, if we let A be 2, -1, 0, 1, or I'm sorry, 1, 0. If we take try to find the eigenvalues by finding the characteristic polynomial, so this will be 2 minus lambda, -1, 1 minus lambda, and this is going to be 2 minus lambda times minus lambda plus 1, which is lambda squared, minus 2 lambda plus 1, which is lambda minus 1 squared. So the only root this could have is 1. Okay, and if we look at lambda equals 1, what we get is we get 2 minus 1, it's 1, -1, 1, -1. Plug this in here to find the null space of this matrix. I think you can see it's very easy. This just gives us x minus y equals 0, so x equals y. And so our only eigenvectors are going to be multiples of 1, 1. Okay, so now we have a little bit of a problem. Like unlike we don't have we can't find two linearly independent eigenvectors. We can find two eigenvectors, and we can find, but they'll be scalar multiples of each other. So it's really, in this case, it's going to be impossible to find a diagonal matrix D and an invertible matrix P so that AP is equal to PD, which is actually equivalent to saying that A can be written as P D P inverse, since if say V1 and V2 are going to be the columns of P, whatever P is, and D is, I don't know, let's say lambda 1, 0, 0, lambda 2. If that's the case, then AP is going to be, well, AP, again, this will be AV1, AV2, and this is going to be lambda V1, lambda 1 V1, lambda 2 V2. And what this of course will mean is that lambda 1 and lambda 2 are eigenvalues, and V1 and V2 are eigenvectors. Okay, assuming that they're non-zero, but then P can't be invertible, because any eigenvectors are going to be multiples of 1, 1. So P is not invertible. Okay, so we can't do it this way. Now, another thing that's different in these examples is you'll notice that the algebraic multiplicity of 1 here was 2, and the geometric multiplicity was 1. So the geometric multiplicity was 1, because this generated all the eigenvectors. The algebraic multiplicity was 2, because we have lambda minus 1 squared. In our previous example, we had that the algebraic multiplicity and the geometric multiplicity were both equal to 1, right? Okay, and that's no accident. Okay, for this nice diagonalizable phenomenon to happen, we need the algebraic multiplicity and the geometric multiplicity of each eigenvalue to be equal to each other. Okay, and we're going to talk about more of that when we get into the theory in the next part of the video. But I just want to give you one more example here. And we're talking about the Fibonacci numbers. Maybe some of you have heard about the Fibonacci numbers or the Fibonacci sequence. It's associated with one of the early math textbooks from the 1200s had a word problem that had to do with rabbits, and how many pairs of rabbits would you have if something happens. And what the problem boils down to is finding this sequence. You have the sequence, which is defined recursively. You have f1 equals, or let's see, let's make sure I do it this way. There are various versions of this. It depends on where you start with, and I want to start with, we'll call it f0 is going to be 0, f1 will be 1, and then fn is going to be fn minus 1 plus fn minus 2 for n greater than or equal to 2. All right, so so basically you just add the previous two Fibonacci numbers. So the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, and 21, and so on, like that. Okay, and the sequences were to note the number of pairs of rabbits after each month. If you know every newborn pair, you know, takes a month to be fertile, and then it produces another pair, you know, every month after that. Okay. Now, we'll see that there's actually a nice formula that will, what we call a closed formula, that will determine what the nth Fibonacci number is without actually having to compute the previous ones, because we can see that Fn minus 1 can be written as the product of the matrix 1, 1, 1, 0 times Fn minus 1, Fn minus 2. Okay, if we think about that, this is when we multiply this out, this is Fn minus 1 plus Fn minus 2, which we said is Fn, and then this is just Fn minus 1. Okay, and this in turn will be 1, 1, 1, 0 times Fn minus 2, Fn minus 3, and so on. And eventually what we get is that this is going to be 1, 1, 1, 0 to the nth power, I think. Yes, to the nth power times 1, 0. Okay, I think hopefully this is true, because if we have 1 and 0 here, well, we want this. Maybe it's n minus 1. Okay, let me just pause for a moment. All right, yes, it was n minus 1. Okay, that's what it should be. N minus 1. So now, so our matrix that we're going to be interested. We'd like to get a formula for this expression, and then multiply it by 1, 0 and get an expression for that. So we can let A be this matrix 1, 1, 1, 0. And if we do the same thing, if we try to find the eigenvalues and the eigenvectors and then find a diagonal matrix and an invertible matrix, what makes everything nice. So A minus lambda I is 1 minus lambda, 1, 1 minus lambda, which is 1 minus lambda minus 1, which is lambda squared minus lambda minus 1. Now, this is a second degree polynomial. It doesn't factor nicely. We have to use the quadratic formula, and in fact the roots are going to be lambda 1 is 1 plus the square root of 5 over 2, and 1 minus lambda 2 can be 1 minus the square root of 5 over 2, which we've seen before in some other lectures. This is the golden ratio. This is its conjugate. I'm just going to call it, so we don't have to keep writing this down, I'm just going to call this omega 1 and this omega 2. Okay, and a couple things that might help when we're doing calculations. We can note that omega 1 plus omega 2 is going to be 1. Omega 1 times omega 2 is going to be negative 1. And omega 1 minus omega 2 is the square root of 5. You can check that. So there's just some tidbits there. But you have now that if we try to find the eigenvectors, if we play omega 1 into here, we get 1 minus omega 1, 1, 1 minus omega 1 times xy equals 0. Since these two rows are actually multiples of each other, they are. It might not look that way, but they're multiplied. If you allow multiplying by irrational numbers, they are. This bottom row tells us that x minus omega 1 y is 0. So x has to be omega 1 y. So we can let y equal 1. And so the matrix, the eigenvector would be omega 1, 1. And you can do the same thing with omega 2. So this is the eigenvector when lambda equals omega 1. And just by basically doing the same calculation, you get omega 2, 1 is the eigenvector for omega 2. And now if we do this, we can let P be the matrix omega 1, 1, omega 2, 1, and if we let D, then D will be omega 1, 0, 0, omega 2. And you can check that P inverse is 1 over square root of 5 times 1 minus omega 2 minus 1 omega 1. You can just use the formula for the determinant of a 2 by 2 matrix, and that's how you get this. We're just factoring out a square root of 5. Okay, well, the nice thing about this is once we get this, after everything's said and done, we get that A is equal to P D P inverse, and that means A to the n is P D to the n, P inverse. And so Fn minus 1 is going to be, well, actually we want this to be n minus 1 here, so this will be P D n minus 1 P inverse times the vector 1, 0. So this is P D to the n minus 1, so this will be omega 1 to the n minus 1, 0, 0, omega 2 to the n minus 1. And then P inverse is 1 minus omega 2, negative 1, omega 1, times the square root of 5, or times 1 over square root of 5, times the vector 1, 0. Okay. And this is just a scalar, so we can bring that out front. And actually, when everything is said and done, what we get is the following. We can get this made. We can just basically multiply everything out. So do we want to do it? Do we have time to do that? I guess we can do that. Well, so this is going to be 1 over square root of 5 times omega 1 to the n plus 0, 0 plus omega 2 to the n, and then omega 1 to the n minus 1, and this is omega 2 to the n minus 1 times this vector 1 minus omega 2, negative 1, omega 1 times 1, 0. And this is going to be, whenever the smoke clears, we're going to have, something, this is going to be Fn, and we'll have something down here which we won't care about. But what we eventually get is that Fn is going to be 1 over square root 5 omega 1 to the n minus 1 over square root 5 omega 2 to the n. Okay, where you have, because you can see when n equals 0, this is just going to be, this will be, this will just be 1, and we'll have something, this will be 0, and if n equals 1, we get the square root of 5 will cancel, and we get 1, and we can go from there. But that holds. So we get this nice explicit formula for the Fibonacci sequence, the Fibonacci numbers, and I think that's kind of cool. So this whole process of representing replacing a matrix with an expression involving a diagonal matrix, that's really a powerful method. And we're going to formalize all of this next in the next lecture. So thank you for your patience, and we'll see you next time.